Hello, this is Jack Jackson. We continue our looking at similar triangles, and this leads us to one of the most important applications of similar triangles, and that's the entire field of trigonometry. The word trigonometry literally means trigon or triangle, measure, and at its core, trigonometry is based on measuring triangles. And we're going to see below, as we go through the next series of several videos, that the main thing that makes trigonometry work is similar triangles. Now, the next several videos and the next section of the notes here are going to have illustrations uh, from a massive Geometry Sketchpad sketch that I created called Trigonometry Ultimate. Unfortunately, Geometry Sketchpad is pretty much defunct now. It's hard to even buy a copy of it. Um, it was a great program, but GeoGebra has kind of surpassed it. And this particular Trigonometry Ultimate sketch contains dynamic applets for an entire course in trigonometry. And what I plan to do is at some point reproduce the constructions there and collect them in Trigonometry Collected Resources GeoGebra book along with the best trigonometry activities I can find. I actually have a student who's planning to complete this task with me. Right now it's the spring of 2024, and she's planning on completing this with me in the fall of 2024. And the following set of videos are also on my trigonometry playlist as well. Um, this material is typically covered both a high school geometry course and a high school pre-calculus course, as well as courses in trigonometry, pre-calculus, and geometry. Uh, I have always include a law of cosines related rate problem in Calculus 1. And so there's a lot of stuff there. So this Trigonometry Unit 1 playlist, which is one of my other playlists you can see on my YouTube channel, has a lot of the same material in it. Okay. And so let's think about some things that we have already looked at. Okay. Earlier we proved the Euclidean triangle angle sum theorem. That's proposition, I guess it was 80, I think. Triangle in a triangle in Euclidean geometry, the sum of the measures of the three interior angles is always pi radians or 180 degrees. Now, I have a task, one more task I'd like you to look at, uh, and I'm going to have you set this up and see if you can come back in the next video and kind of look at this. But I want you to try to do this on your own, and it's going to lead you to a really famous theorem. It's going to be hiding in this construction here. So let's start by constructing a general right triangle ABC with the right angle at C. Then measure the sides and use the following label. Lowercase a is the length BC, lowercase b is the length AC, and lowercase c is the going to be the length of the hypotenuse AB. Measure the remaining angles, and then construct an altitude C D. That line segment's an altitude. Let H be the height of the triangle where we're considering AB is the base, right? And so that would be the length CD. Let's let X be the distance from A to D, and then see if you can come up with a formula for the distance from B to D uh, in terms of the letters A, B, C, H, and or X. See if you can figure out what it would be. Then measure H and X in your GeoGebra sketch. This is something for you to do in GeoGebra. Measure the angles of the three triangles which are formed. What do you notice about the three triangles? Test out your conjecture by manipulating the vertices A, B, and C. Then prove your conjecture. Using the three triangles and the proposition you just proved, write down two different proportions, a fraction equal to another fraction, and solve for X. If you know about sine and cosine already, one hint would be to think of two different ways to express sine of the angle B, or the sine of the angle. B is the I guess is the label for the angle, and it's the measure of that angle that would be the sine of it. But anyway, we can use b for both the label for the vertex, the angle, and its measure. And then cosine of b, also two different ways of doing it to set up two fractions equal to you. And we're going to be using a couple of different right triangles for these. And then solve both of these for x and substitute and simplify. And state the final result as a proposition, being careful to state the appropriate hypothesis and conclusion. And then I think you probably know the name of this. So what's the name of this famous theorem that you just proved if you actually did all these steps and justified everything? Then state the converse and then prove the converse. And here's kind of an outline for the proof of the converse. Construct a triangle with sides of length lowercase a, b, and c with the appropriate relationship among the sides. Construct another triangle with the appropriate angle measures, with an appropriate angle measure there between the lengths, sides of length a and b, and have it have lengths a and b, and show those two triangles are congruent and reach your conclusion. If you've done the first part, this will make a little more sense, and then see if you can work that out. So carefully state the full theorem as an if and only if statement, and hopefully at this point then you've got a proof of this very famous theorem. One direction at least makes use of some similar triangles. And come back in the next video and I'll show you the proof of it, but see if you can do it on your own first.